A new rock has been spotted hurtling toward the moon. Its size and path have set alarms among astronomers. We now watch it closely. The first indication of the object came from the Pan-STARRS 1 telescope on March 12, 2024. Its moving point stood out against the background stars during routine sky mapping. The detection prompted the automated system to flag it as a potential near-Earth body. Automated pipelines issued an alert that reached the Lowell Observatory within hours. Observers there scheduled a series of longer exposures on the 4.3-meter reflector. The resulting images confirmed a faint, steady source moving along a consistent track. Photometric analysis showed a rotation period near 12 hours, indicating a relatively slow spin. Light curve amplitude stayed low, implying the body is not highly elongated. Such a shape often points to a rubble pile structure held together by self-gravity. Brightness modeling placed the diameter close to 1.5 kilometers, roughly the height of Mount Everest. That length stretches from sea level to the summit of Earth's tallest peak. In other words, the asteroid rivals the most prominent mountain on our planet. In astronomical terms, the rock remains tiny. Ceres spans about 950 kilometers across. Our object measures roughly 1/100th of that, yet it is massive for a near-Earth asteroid. Size alone makes it a priority for planetary defense surveys. Orbit determination gave a semi-major axis of 1.1 AU, an eccentricity of 0.22, and an inclination near 5 degrees. These elements place the perihelion just inside Earth's orbit and the aphelion beyond Mars. Such an ellipse ensures the asteroid crosses Earth's neighborhood twice each year. Future observations during the next opposition will test this orbital model against reality. The orbital plane intersects the Moon's orbital plane twice annually, creating narrow windows for a possible encounter. Calculations show the asteroid will pass within 0.03 AU of the Moon during the 2032 approach. That distance corresponds to roughly 11 million kilometers, still close enough to consider impact risk. Current simulations assign a 0.03% chance of impact before the end of the century. While the number is small, the potential consequences of a lunar collision merit careful monitoring. Even a low probability event can dominate risk assessments when outcomes are severe. I find it hard to picture how a rock of this size could miss the Moon entirely during those brief windows. The geometry feels precarious, yet orbital mechanics often produce surprising outcomes. Small changes in velocity could shift the encounter from a near miss to an impact. A shift of just a few centimeters per second could change the outcome dramatically. A lunar impact would eject a plume of debris into space, some of which could intersect Earth's orbit. Even a modest dust cloud could increase meteor activity for years, affecting satellite operations. The long-term consequences depend on particle size and dispersion pattern. Large near-Earth objects have visited the inner solar system throughout history, leaving scars on planetary surfaces. The 1908 Tunguska event, though only a few hundred meters across, flattened a forest of 2,000 square kilometers. That episode shows how relatively small bodies can cause regional devastation. The asteroid Apophis, discovered in 2004, sparked similar concern when early orbits suggested a 2029 Earth approach within 30,000 kilometers. Subsequent observations refined its path, removing any impact risk for the next century. Apophis serves as a reminder that early uncertainties can be resolved with more data. Unlike Apophis, 2024 YR4's trajectory brings it close to the Moon rather than Earth, shifting the focus of risk assessment. The Moon's lower gravity means ejecta can achieve higher escape velocities than from Earth. Consequently, more material may travel toward Earth's neighborhood. Monitoring programs such as NASA's Planetary Defense Coordination Office and ESA's Near-Earth Object Coordination Center scan the sky nightly for similar threats. Their catalogs now contain thousands of objects larger than 140 meters, each tracked with orbital uncertainties. Continuous updates keep the impact probability of 2024 YR4 under close review. The databases are refreshed weekly, ensuring that any new measurements immediately affect risk calculations. Ground-based radar, especially the upgraded Arecibo-like system in Puerto Rico, provides precise range and velocity data for close approaches. Radar echoes from 2024 YR4 have already refined its distance to within a few hundred meters. This level of precision sharpens predictions of future lunar proximity. I don't quite trust a single model when chaotic forces can nudge the orbit over decades. Small forces such as solar radiation pressure and the Yarkovsky effect can accumulate, altering the trajectory subtly. Accounting for these factors requires long-term observation and sophisticated numerical integration. We don't really know the asteroid's exact mass, which depends on its composition and internal porosity. Spectral measurements suggest a carbon-rich surface, typical of C-type asteroids common in the outer belt. This composition hints at a relatively low bulk density. Assuming a bulk density of 1.4 gcm3, the object's mass would be on the order of 10-13 kilograms. An impact at lunar escape velocity would release energy comparable to several hundred megatons of TNT. Such an explosion rivals the most powerful thermonuclear weapons ever tested. The energy release could carve a crater several kilometers across, reshaping the local lunar landscape. Ejecta would likely reach altitudes of tens of kilometers before falling back, forming a temporary dust halo. Over time, this material would settle, darkening the surrounding regolith. Even a modest shift in the moon's mass distribution can alter its libration, a subtle wobble observable from Earth. Detecting such changes requires laser ranging with millimeter precision, a capability achieved by several global stations. Present uncertainties are still larger than any shift a single impact could cause. Current lunar laser ranging stations report position uncertainties of a few millimeters, far below any measurable impact effect. Consequently, we cannot yet observe the subtle orbital adjustments a collision might produce. Ongoing upgrades aim to push precision toward the sub-millimeter regime. Future facilities like the Vera C. Rubin Observatory will increase detection rates of small bodies dramatically. More frequent observations will tighten orbital solutions for objects such as 2024 YR4, shrinking uncertainty clouds. Each new data point nudges the predicted path closer to reality. Even with perfect data, chaotic dynamics keep absolute certainty out of reach. Small variations in the Yarkovsky effect can shift the asteroid's semi-major axis by a few meters per year. Over centuries, those shifts compound, altering the timing of any lunar approach. For now, the asteroid glints faintly against the evening sky, a speck barely above the horizon. Its slow motion across the twilight reminds us how vast the space between Earth and Moon truly is. I note the way the faint point seems to pause before fading. Tonight, a thin crescent moon will sit just beyond, casting a faint glow on the horizon. The moon looks like a dead rock, but its surface tells a story of constant bombardment. Without air or weather, every incoming stone leaves a scar that never washes away. That makes the moon a surprisingly open target for any object that crosses its orbit. The rock that covers the moon is a mix of fine powder and jagged shards. The powder, called regolith, feels like sifted ash, only a few centimeters deep in most places. When a meteor strikes, there is nothing to slow it down. The kinetic energy goes straight into breaking rock and throwing debris outward. On Earth, most small bodies burn up in the atmosphere. The same stone that would flare as a shooting star on our sky hits the moon at full speed. I find it hard to picture that raw speed hitting a powdery plane. The rate at which the moon collects impacts is higher than you might think. Studies of crater counts suggest that the moon receives roughly one impact large enough to leave a 1-kilometer crater every few 100,000 years. By contrast, Earth's surface is constantly reshaped by wind, rain, and plate motion, erasing many older marks. The ancient basins we see from orbit are proof that the moon has survived far larger collisions. Those scars remain sharp, their rims still casting shadows in the low lunar sun. The Earth's gravity pulls nearby objects toward the combined Earth-Moon system, slightly increasing the number of projectiles that reach the moon. It is a subtle effect, but calculations show that the moon's impact flux is about 20% higher than it would be without Earth's pull. That makes the moon a bit more of a collector than a lone rock drifting in space. The lack of an atmosphere also means that ejecta from an impact can escape the moon's weak gravity. When a large asteroid hits, a plume of molten rock and vapor shoots up, some of it reaching speeds above the lunar escape velocity of 2.4 ms. That material can travel on ballistic arcs, some falling back, some entering orbit, and a fraction heading toward Earth. A base built in a crater may enjoy natural shielding, yet the same crater walls could focus secondary fragments toward the settlement. Engineers will need to consider shielding that can stop high-velocity micrometeoroids, perhaps using layers of regolith piled over habitats. The very material that records past impacts could become a protective blanket. The moon's surface also offers a laboratory for studying impact physics without atmospheric interference. By placing seismometers near a fresh crater, scientists could watch how shock waves travel through the brittle crust, learning how energy dissipates in a vacuum. Because the moon retains every crater, we can count them to infer the history of the inner solar system. The distribution of crater sizes tells us about the population of near-Earth objects over billions of years. That record is a baseline against which we compare the current flux of asteroids, helping us gauge how unusual an event like a kilometer-scale impact would be today. Yet there are limits to what the lunar record can reveal. Some older craters have been flooded by later lava flows, erasing their rims. Others sit in permanently shadowed regions where we cannot see them with ordinary cameras. We don't really know how many impacts have been hidden beneath the dust in those cold traps. Those subtle variations are still being measured. The moon's role as a target is also shaped by its orbital dynamics. Still, the same geometry means that a projectile arriving from the direction of Earth's shadow may be hard to detect until it is very close. That uncertainty adds a layer of risk for any future outpost. The surface temperature swings from blistering heat to bone-cold darkness, which affects the strength of the regolith. In the sun, the top layer can become hard as glass. In the shade, it behaves like a loose powder. An impact on a hot, compacted surface will produce a different ejecta pattern than one on a cold, fluffy one. In laboratory simulations, researchers fire projectiles at basalt targets in vacuum chambers. Still, scaling those experiments to kilometer-scale impacts involves assumptions that we can't fully test. I find it hard to picture a single impact reshaping a whole lunar hemisphere. The moon's vulnerability is not just a curiosity, it is a practical concern for Earth as well. If a massive impact throws enough debris into a trajectory intersecting Earth's orbit, some fragments could survive the trip and enter our atmosphere. Most would burn up, but larger pieces might reach the ground, adding a secondary hazard. That chain of cause and effect is why monitoring near-Earth objects matters. Even a modest impact could alter the moon's orbit ever so slightly. The exchange of momentum between the impactor and the lunar surface would change the moon's speed around Earth by a fraction of a millimeter per second. Over millions of years, such tiny nudges could accumulate, but the effect is negligible for human timescales. Finally, the moon's exposed nature lets us test mitigation techniques directly. A small kinetic impactor could be sent to the moon to see how much momentum is transferred, providing data for future planetary defense strategies. The clear view of the impact plume, unblurred by atmospheric scattering, would give a precise measurement of ejecta mass and velocity. That experiment would be a straightforward way to calibrate our models. The quiet, airless world of the moon therefore serves as both a record keeper and a testing ground. Its surface composition, lack of weather, and gravitational relationship with Earth combine to make it a surprisingly receptive target for space rocks. As we plan to live there, we must keep those facts in mind, lest the very scars that tell the moon's story become a hazard for the next generation of explorers. The last thing I noticed before turning off the monitor was a tiny, fresh-looking pit near the rim of a larger crater, its edges still sharp against the surrounding dust. The kinetic energy of an impact is the first number that forces a pause. Mass equals volume times density, so a 500-meter sphere of typical stony material, about 3,000 kilograms per cubic meter, carries roughly 2 times 10^11 kilograms. If it strikes the moon at 20 kilometers per second, about the speed most near lunar objects retain after escaping Earth's pull, the energy calculation is straightforward: a half mv2. Plugging the figures in yields around 4 times 10^19 joules, a figure that translates to almost 10,000 megatons of TNT. It is a number that feels abstract, and I find it hard to picture a single blast that large without the mind slipping into exaggeration. What matters, however, is that the energy is released in a fraction of a second, turning kinetic motion into pressure, heat, and motion of the lunar surface. When the asteroid's front face meets the regolith, a shock wave shoots outward at several kilometers per second, far faster than any seismic wave we have measured on Earth. The lunar soil, a powdery mix of glassy fragments and breccia, transmits the shock with a sound speed of roughly 2 kilometers per second. At the instant of contact, the pressure spikes to tens of gigapascals, enough to crush rock into a glassy melt in an instant. The wave decays as it spreads, but the initial spike determines how much material is instantaneously compressed. Because the moon lacks an atmosphere, there is no cushion to soften the front. The shock travels directly into the solid surface. We don't really know the exact fraction of the incoming energy that ends up as peak pressure versus heat, but laboratory experiments on analog materials suggest a split of roughly 60% into pressure, 30% into heat, and the remainder into kinetic ejection of fragments. Heat generated by the impact is enormous. Even a modest fraction of the 4 times 10^19 joules raises the temperature of the affected rock above its melting point, creating a pool of molten silicate that can vaporize a thin layer of the target. Estimates based on melt production models put the melt volume at several cubic kilometers, while the vapor plume may contain a few 100 million tons of gas phase material. The vapor does not escape the moon's weak gravity easily. Most of it will fall back, forming a transient, tenuous cloud that settles in minutes. The remaining ejecta, launched at speeds exceeding 2 kilometers per second, follows ballistic arcs that can reach far beyond the impact basin. Because lunar escape velocity is only 2.4 km/s, a small fraction of the fastest fragments will leave the moon entirely, entering an orbit around Earth-Moon space. Crater size follows scaling laws that have been refined over decades of impact experiments and observations of planetary surfaces. One commonly used relation expresses the final crater diameter d as a product of impactor size, velocity, target gravity, and material strength. D approximately K, a m slash rho T3 V, G Tudu, where K is an empirical constant, rho T the target density, V the impact speed, and G the surface gravity. For the Moon, G is about 1/6 that of Earth, which allows larger craters to form from a given energy. Applying the formula with the numbers above gives a transient cavity roughly 30 kilometers across. The final rim, after collapse and slumping of the walls, may settle near 25 kilometers in diameter. That size places the hypothetical crater among the Moon's mid-range basins, comparable to the well-studied Copernicus crater, but far smaller than the massive South Pole Aitken Basin. Putting the result next to the Chicxulub event helps to anchor the scale. Chicxulub's impactor, about 10 kilometers in diameter, released on the order of 1023 joules, roughly 2,500 times more energy than our 2024 YR4 scenario. Its crater spans roughly 150 kilometers, while the lunar basin we predict would be a fraction of that. The difference illustrates how sensitive crater dimensions are to both impactor size and the gravitational pull of the target body. Beyond the simple numbers, the physics of the collision includes a cascade of secondary processes. The shock wave, after passing the initial compression stage, reflects off the crater floor, generating tensile stresses that fracture the rock. Those fractures become the pathways for melt to flow outward, carving the characteristic terraces seen in lunar basins. At the same time, the rapid depressurization of the vapor plume can drive a brief, low-pressure wind across the surface, a phenomenon that has no analog on Earth because of our dense atmosphere. One lingering uncertainty is the exact proportion of impact energy that converts into ejecta kinetic energy. Laboratory shots into sand or basalt suggest a range of 20 to 30%, but scaling those results up to kilometer-scale events introduces ambiguities. We don't really know how the Moon's unique regolith, with its sharp, angular grains, alters that balance compared with the more cohesive rocks tested on Earth. If the impact were to occur near the lunar far side, the ejected debris would have a different fate than if it struck the near side. Fragments launched toward Earth could intersect the planet's orbit, posing a low probability but non-zero risk of meteoritic delivery. Conversely, material thrown outward on the far side would likely remain in lunar orbit, slowly grinding down through micrometeoroid impacts. The final observation that stays with me is the thinness of the lunar regolith at the impact site, often only a few meters deep. Yet the shock wave will instantly compress and melt material down to several kilometers, exposing a fresh slice of the Moon's interior that has lain hidden since the early days of the solar system. The impact begins with a flash of kinetic energy, a momentary surge of pressure that compresses lunar regolith like a fist on soft dough. In those first seconds, the projectile, a kilometer-wide chunk of rock, pierces the surface, and the target material responds as a fluid would under a sudden squeeze. I note the formation of a transient cavity, an expanding, roughly hemispherical void that grows at several hundred meters per second. The walls of that cavity collapse inward, their motion governed by the same excavation flow that drives sand in a sand blasting experiment. The excavation flow is not a smooth, laminar stream. It is a chaotic surge of particles, each grain jostling its neighbor, some lofted upward, others hurled sideways. The shock front pushes material outward, carving a bowl that reaches depths of several kilometers before the pressure wave weakens. I find it hard to picture the exact shape of that flow. The equations predict a parabolic profile, yet the real surface is littered with fractures that disrupt any perfect symmetry. When the transient cavity reaches its maximum size, the lunar crust can no longer support the void. The floor of the cavity rebounds, a process I record as central uplift formation. The rebound is a brief, violent push upward, sending a mound of rock toward the surface. In larger impacts, this uplift does not remain a simple peak. Instead, it collapses into a ring of peaks that encircle the crater's center. The resulting structure, a peak ring, marks the boundary between the deepest excavated material and the shallower layers that were merely displaced. The peak ring is not a smooth ridge. It is a jagged necklace of blocks, some tens of meters across, each bearing the scars of the shock. Their composition often differs from the surrounding mere basalt, hinting that the impact has drawn material from deeper strata. I admit that we do not really know the exact depth from which each block originates. Seismic data from past missions provide only coarse constraints. Beyond the peak ring, the ejecta blanket spreads outward like a thin, powdery carpet. The blanket's thickness drops sharply with distance, but its reach can extend for hundreds of kilometers. I picture the particles as a cold, fine dust that settles in a radial pattern, each grain retaining a faint memory of the velocity it once carried. The distribution is not uniform. The downrange side, where the impactor arrived, receives a denser layer while the uprange side is left with a thinner veil. The ejecta blanket also carries larger fragments, some of which escape the moon's weak gravity entirely. Those high-velocity rocks become temporary moons, orbiting for a few days before either colliding with Earth or burning up in the solar wind. The loss of mass is minuscule on a planetary scale, yet it reminds us that a single impact can seed the surrounding space with debris. One of the more striking consequences of such a massive crater is the potential exposure of mantle material. The moon's crust is only a few tens of kilometers thick beneath the mare regions, and a crater deeper than that can pierce through to the mantle. If mantle rock reaches the surface, it would appear as olivine-rich outcrops, darker and denser than the surrounding basalt. Detecting those outcrops would require spectroscopic analysis, but the very act of exposing mantle material offers a rare window into the moon's interior. The exposure, however, is fleeting. Lunar weathering, micrometeorite impacts, solar wind sputtering begins to erode the fresh mantle surface almost immediately. Within a few thousand years, the mantle outcrops will be covered by a new layer of regolith, indistinguishable from the older surface. This rapid burial is part of the long-term crater degradation processes I track in my notes. Degradation proceeds through several stages. First, the rim of the crater, initially a sharp raised edge, is softened by countless tiny impacts. Each micrometeorite chips away at the rim, rounding its profile. Next, thermal cycling, daytime heating to over 100 degrees Celsius, nighttime cooling to -100, induces stress fractures that gradually crumble the rim's rock. Over millions of years, the crater floor fills with impact melt and later with fine regolith, turning a deep basin into a shallow depression. Even as the crater degrades, the peak ring may persist as a subtle rise, a reminder of the original impact's magnitude. I sometimes wonder whether the ring's remnants could be mistaken for a separate geological feature in remote sensing data. The answer, I suspect, lies in careful analysis of crater morphology, but the line between a degraded peak ring and a small, unrelated dome can be blurry. Throughout this sequence, the sound of the impact is absent. There is no atmosphere to carry a shock wave. Yet the energy is audible in the vibrations that travel through the lunar crust, a silent tremor that would register on seismometers as a sharp, high-frequency spike. Those vibrations propagate outward, reflecting off the moon's interior boundaries, creating a complex pattern of echoes that scientists could, in principle, decode to map the interior structure. In my notebook, I sketch the sequence as a series of cross-sections. The transient cavity, the central uplift, the peak ring, the ejecta blanket, and the eventual infilling. Each line represents a moment in time, a snapshot of a process that unfolds over seconds, minutes, and then millennia. The diagrams are crude, but they capture the essential geometry that governs the crater's birth. I have to acknowledge that many details remain uncertain. The exact thickness of the transient cavity's walls, the precise composition of the uplifted material, the size distribution of ejecta, all depend on the impactor's angle, velocity, and internal structure. Laboratory experiments with high-velocity projectiles give us clues, yet scaling those results to a lunar scale event introduces uncertainties that we cannot fully eliminate. Still, the overall picture is clear. A massive impact carves a gigantic crater, reshapes the surface, briefly reveals deep material, and then begins a slow, inexorable process of erosion and infill. The crater's birth is a violent, brief episode, but its afterlife stretches across geological epochs, leaving a scar that tells a story of force and transformation. One small detail catches my eye as I close the entry. A solitary basalt fragment, still warm from the impact, rests half a meter from the inner rim, its surface bearing a faint, glassy sheen that hints at the fleeting heat of the event. When a body the size of 2024 YR4 slams into the moon, the surface does not simply crumble. It erupts in a spray of rock, glass, and vapor that spreads in every direction. The first thing a scientist notes is the velocity spectrum of the ejecta. Near the impact point, material is launched at several kilometers per second. Farther out, speeds drop to a few hundred meters per second. I find it hard to picture a single event producing such a wide range, but laboratory experiments with high-velocity projectiles show similar spreads. At the moment of contact, the kinetic energy converts to pressure, shattering the crust. The shattered fragments form a transient cloud that expands like a puff of smoke in a vacuum. The cloud is dense enough to scatter sunlight, creating a brief, faint halo around the new crater. Because the moon lacks an atmosphere, nothing slows the particles once they are airborne. Each fragment follows a ballistic path dictated by its launch speed and the moon's gravity. The lower velocity grains settle within a few minutes, coating the surrounding plane with a thin layer of fresh regolith. Higher speed chunks travel farther before gravity pulls them back. Some reach the far side of the moon, striking the opposite hemisphere after a half-orbit. The pattern of secondary craters can be traced back to the original impact, a useful clue for field geologists. The critical speed for escape is about 2.38 km/s. Anything faster than that leaves the lunar sphere of influence entirely. In a typical impact of this magnitude, perhaps a few percent of the total mass exceeds that threshold. I don't really know the exact fraction. Simulations vary with impact angle and composition. Escaping debris follows a hyperbolic trajectory around Earth. Some particles enter Earth crossing orbits, others become temporary satellites of the planet. Their fate depends on subtle gravitational nudges from the Sun and Earth's own pull. The chaotic nature of those paths makes precise prediction difficult. If enough material reaches a stable orbit, a tenuous ring could form around the moon. The idea sounds exotic, but the physics is straightforward. Particles that do not re-impact will spread along the lunar orbit, gradually dispersing. The density would be far lower than Saturn's rings, perhaps detectable only by a dedicated dust sensor. Such a secondary ring would be short-lived. Solar radiation pressure and micrometeoroid impacts would erode it within decades. Still, its brief existence could interfere with low-altitude spacecraft. Even a sparse cloud can pose a micrometeoroid hazard to delicate optics. Future lunar missions would need to account for that hazard. Landing sites near the new crater might be littered with sharp shards, increasing abrasion on wheels and seals. Habitat designers would have to consider a higher background of dust deposition, especially if the ejecta cloud lingers for hours. Astronauts on the surface would notice a fine, gritty haze settling after the impact. The dust would cling to visors and tools, making routine tasks messier. In the absence of wind, the particles would remain where they land until disturbed by human activity. The temporary debris cloud also affects radio communications. A dense enough cloud can attenuate certain frequencies, leading to brief signal loss for orbiters passing overhead. Engineers would need to schedule critical data transfers outside the cloud's peak density window. From a scientific standpoint, the ejecta provides a natural sample of deep lunar material. Material launched at the highest speeds originates from several kilometers beneath the surface, offering a glimpse of layers otherwise inaccessible. Collecting that material could inform models of lunar formation. However, retrieving samples from the cloud is not trivial. The particles travel at speeds that would destroy most collection devices on impact. One could imagine a fast-moving net deployed from an orbiter, but the engineering challenges quickly become apparent. The distribution of particle sizes also matters. Fine dust, less than a millimeter, dominates the mass of the cloud, while larger boulders carry most of the kinetic energy. The fine fraction can stay aloft longer, forming a diffuse veil that persists for hours. The boulders, in contrast, follow more direct arcs and land quickly. Temperature variations add another layer of complexity. Ejecta that lands on the night side of the moon will cool rapidly, potentially forming a thin frost of volatile compounds. On the sunlit side, the same material will heat, possibly vaporizing some components and adding to the transient exosphere. The impact also excites seismic waves that travel through the moon's interior. Those waves can loft loose regolith in distant regions, contributing to a secondary, low-energy dust cloud. Seismometers placed far from the crater would record a long tail of tremors, a reminder that the moon is not a static body. In the weeks following the event, the most energetic particles have already escaped, and the majority of the cloud has settled. Yet a faint trail of dust continues to orbit the moon, slowly spiraling inward under the influence of Earth's gravity and solar radiation. Detecting that trail would require a sensitive dust detector on a lunar orbiter. The presence of lingering debris also influences the planning of future habitats. Engineers might choose to site modules on higher ground, away from the expected deposition zone. Even a modest rise of a few meters can reduce the thickness of the dust blanket that would otherwise accumulate. Radiation shielding could be affected as well. A thin layer of fresh regolith can provide additional protection against galactic cosmic rays, but only if it is compacted. Loose dust offers little attenuation, and its electrostatic charge can interfere with surface instruments. From a broader perspective, the ejecta illustrates how a single impact reshapes the lunar environment on multiple scales. It is a reminder that the moon, though seemingly inert, responds dynamically to external forces. The cascade of effects, from high-speed particles to subtle dust veils, spreads outward like ripples in a pond. If we consider the long-term evolution, the material that escapes the moon may eventually rain down on Earth as meteoric dust. Over geological timescales, such contributions are minuscule, but they add a faint lunar signature to our atmosphere. The idea is almost poetic, though the numbers are tiny. Monitoring the ejecta cloud would rely on a network of cameras, LiDAR, and dust detectors. Each instrument captures a different facet: visual brightness, particle density, and velocity distribution. Combining those datasets yields a coherent picture of how the material spreads. The data also feed back into impact models, refining our estimates of crater size, ejecta volume, and escape fractions. Those models, in turn, improve risk assessments for future missions. It is a loop of observation, theory, and application that keeps the field moving forward. One practical concern is the effect on existing lunar infrastructure. If a base were already operating near the impact site, the sudden influx of high-velocity debris could damage solar panels, antennae, and external modules. Protective shielding would become a priority in the design phase. Even small, seemingly harmless particles can cause damage over time. Micrometeoroid impacts on spacecraft have been known to erode surfaces, alter thermal properties, and create tiny pits. A sudden increase in particle flux amplifies those risks for a limited period. The ejecta's composition also tells us about the impactor itself. By analyzing the mixture of lunar and asteroid material in the cloud, scientists can infer the asteroid's makeup, whether it was a carbonaceous chondrite, an iron-rich body, or something else. That information is valuable for planetary defense strategies. In practice, separating the two sources requires careful spectroscopic measurements. The lunar material has a known signature. Any deviations point to the impactor's contribution. The challenge lies in the brief window before the cloud disperses. Beyond the immediate aftermath, the redistribution of surface material may alter the moon's albedo locally. A fresh, darker ejecta blanket can absorb more sunlight, slightly warming the area. Conversely, a brighter, pulverized layer could reflect more light, causing a minor cooling effect. These thermal changes are subtle, but they could influence local temperature gradients, which in turn affect the stability of volatiles in permanently shadowed regions. A shift of even a few degrees can change the sublimation rate of trapped ice. Finally, the impact reminds us that the moon is not an isolated system. Its interaction with Earth, the Sun, and interplanetary debris creates a complex web of exchanges. The ejecta is a visible thread in that web, linking a violent collision to distant, quieter processes. A single grain, lofted from the crater rim, may travel for weeks before settling on the far side of the moon, unnoticed except for the faint trace it leaves in a high-resolution image. When a rock the size of a small mountain slams into the moon, the impact does not stop at the scar it leaves. The collision delivers a blunt shove, a transfer of momentum that nudges the lunar body away from the path it has followed for billions of years. In a laboratory notebook, I would write the impulse as the product of the asteroid's mass and its impact velocity, then divide by the moon's mass to get a change in speed. The numbers are small compared to orbital velocity, perhaps a few centimeters per second, but even that tiny push can shift the orbit by thousands of kilometers over centuries. The shift works like a gentle tap on a spinning top. The moon's orbital energy changes, and the semi-major axis either expands or contracts depending on the direction of the impulse. If the impact adds forward momentum, the orbit lifts. If it steals a little, the orbit drops. A higher orbit means a longer month, a slower dance around Earth. A lower orbit shortens the month, bringing the moon closer to the tides it already pulls. I find it hard to picture the exact change in distance, because the numbers hide behind the scale of the system. A few thousand kilometers sound large, yet they are a fraction of the 384,000 kilometer average gap. Still, the Earth feels that change in the pull of the lunar tide. Tidal forces scale with the inverse cube of distance, so a modest orbital shift reshapes the bulge of ocean water that rises twice a day. The bulge becomes a shade taller or a shade flatter, and the timing of high tide slides by minutes. Those tides are not just surface ripples, they are a conduit for angular momentum between Earth and Moon. The Earth's rotation drags the oceans drag the Moon, and the two bodies trade spin for orbital speed. When the Moon's orbit moves, the balance of that trade moves too. A higher orbit requires the Earth to give up a little more spin, lengthening the day by perhaps a few milliseconds. A lower orbit does the opposite, shaving a fraction of a second from the length of a day. The effect is subtle, buried beneath the daily grind of weather and human clocks, but the physics does not forget. The change also reaches into the moon's own wobble, its libration. Because the moon does not keep the same face perfectly fixed, observers on Earth see a slow rocking back and forth. An orbital shift alters the geometry of that rocking. The amplitude of the libration could increase by a few arc minutes, making a few extra craters peek over the limb. The pattern of the wobble would adjust, and the timing of when a particular region becomes visible would drift. At the heart of the system lies the Earth-Moon barycenter, the point about which both bodies orbit each other. Its location sits inside Earth, about 4,600 kilometers from the center, because Earth's mass outweighs the Moon's. When the Moon's orbit changes, the barycenter shifts slightly. If the Moon climbs higher, the center of mass drifts a little farther from Earth's center, pulling Earth's own path around the Sun into a minuscule wobble. If the Moon drops, the barycenter slides inward and Earth's solar orbit tightens fractionally. The shift is measured in centimeters, yet it is a real, calculable motion. These motions are not independent. They feed back into each other. A changed barycenter nudges Earth's orbit, which in turn tweaks the solar tidal forces acting on the Moon, which can further adjust the lunar orbit. The chain is long, but each link is weak. In a lab note, I would mark the uncertainties with a question mark. Because the exact coupling depends on ocean depth, mantle viscosity, and the precise angle of impact, variables we cannot pin down from a single event. We don't really know how the Earth's rotation would respond over millennia. Short-term measurements would catch a millisecond change, but long-term feedbacks from core mantle coupling could amplify or dampen that shift. The same applies to tidal friction. The oceans may absorb the extra energy differently if continental configurations change. The model space is crowded, and the impact adds just one more point of uncertainty. Even the simplest observable consequence might be a change in the Moon's apparent size at perigee. A higher orbit makes the Moon look a shade smaller, a lower orbit a shade larger by a few percent. That tiny difference would be recorded by astronomers who track lunar angular diameter night after night. The data would sit alongside the impact notes, a reminder that a single rock can set a cascade of motions into motion. A single grain of dust on the lunar surface, flung outward by the impact, may one day return to Earth as a meteor. Its path would be altered by the shifted barycenter, by the slightly different Earth-Moon distance, and by the changed rotation period. The rock would carry with it a record of the impact's momentum, a silent witness to the subtle reshaping of the Earth-Moon system. I keep a mental ledger of every particle that could slip from the Moon into our gravity well. When a massive impact throws rock and dust outward, a fraction of that debris follows a trajectory that intersects Earth's orbit. The Moon's escape velocity is modest, so the ejecta already carries enough speed to become a temporary satellite of the Sun before Earth's pull recaptures it. Estimates for a 10-kilometer impact suggest a dust plume of several 100 million tons, most of it in grains smaller than a millimeter. Those grains do not arrive as a single cloud. Gravity stretches the plume into a long ribbon, and solar radiation pressure spreads the smallest particles over weeks. By the time the ribbon brushes past Earth, the bulk of the mass has been ground down to silicate dust comparable in size to volcanic ash. I find it hard to picture how many of those particles survive the journey without melting. The calculations show that only those under a few microns retain their original form. When the dust reaches the upper atmosphere, it encounters air that is still thin enough to let it glide rather than plunge. The particles decelerate over several seconds, heating the surrounding gas by a few degrees at altitudes near 100 km. That heating is localized, but if the influx were sustained for days, The cumulative effect could raise the temperature of the mesosphere by a fraction of a degree. The change is subtle, but it would alter the chemistry that governs noctilucent clouds. The same ribbon of debris also seeds a series of micro-impacts. Each grain that survives to lower altitudes strikes at tens of kilometers per second, releasing a tiny flash of light and a puff of ionized gas. To an observer on the ground, these events appear as a faint, diffuse meteor shower, far dimmer than the Leonids but spread over a much longer period. The frequency could climb to several thousand impacts per hour, enough that radar stations would register a steady background of echoes. I have watched similar patterns in the data from past meteor storms. The 1999 Leonid outburst, for instance, produced a measurable increase in ionospheric electron density. Those spikes are not dramatic enough to disrupt communications, yet they remind us that even minute particles can perturb the delicate balance of the upper atmosphere. The lunar dust would behave in the same way, only the source would be a single, distant explosion rather than a swarm of comet fragments. Historical analogues provide a rough guide, though none match the exact scenario of lunar ejecta. The 1908 airburst over Siberia injected a burst of fine material that settled over a wide area, leaving a thin layer of soot and raising atmospheric opacity for weeks. That event was a single, high-energy impact on Earth, not a prolonged dust rain, but the lingering haze shows how extraterrestrial particles can linger in the stratosphere. A more recent example comes from the 2013 Chelyabinsk meteor. Its debris cloud caused a brief increase in atmospheric dust that was detected by satellite sensors. Both cases illustrate that the atmosphere can hold onto foreign particles long enough to affect climate models. When I compare those episodes with the projected lunar dust influx, the scale looks larger in total mass but smaller in instantaneous concentration. The dust would be spread thinly across the globe, forming a faint veil that might be detectable only by sensitive LiDAR instruments. Its optical depth would be low, perhaps enough to dim the stars by a few percent at night. That dimming would not threaten agriculture, but it would be a measurable signature of an extraterrestrial event. From an infrastructure perspective, the risk assessment hinges on three factors: the size distribution of the particles, their entry velocity, and the altitude at which they deposit their energy. Modern satellites orbit at altitudes that overlap with the dust's arrival zone. Even sub-millimeter fragments can puncture thin solar panels or erode protective coatings over time. A sustained rain of such particles would increase the wear rate of spacecraft surfaces, shortening mission lifetimes by months or years. Ground-based power grids are less directly exposed, but the ionization caused by the micro-impacts can amplify geomagnetic disturbances. During a strong solar storm, the added ionospheric irregularities from lunar dust could worsen the propagation of high-frequency radio waves, leading to brief outages for aviation navigation. The effect would be modest, perhaps a few minutes of degraded signal, but it would be an additional variable for operators already coping with space weather. I do not have a precise answer for how much the dust would alter global temperature trends. Climate models can insert a thin aerosol layer and watch the radiative forcing shift, but the uncertainty in particle composition and distribution leaves a wide margin of error. We don't really know whether the net effect would be a slight cooling from increased albedo or a marginal warming from infrared absorption. The answer likely sits somewhere in between, and it would be swamped by natural variability. What remains clear is that the Earth-Moon system is not a closed loop. An impact on the Moon can send material our way, and that material can leave subtle fingerprints on our atmosphere and technology. The chain of cause and effect is long, and each link is fragile. A single grain, traveling at 30 kilometers per second, can spark a cascade of micro-events that we can only begin to catalog. In the quiet of a high-altitude observatory, a spectrometer once recorded a faint, persistent line at 550 nanometers that did not match any known atmospheric constituent. It lingered for weeks after a simulated dust injection, hinting at a mineral signature that might belong to lunar basalt. The moment a sizable fragment of 2024 YR4 strikes the moon, the first thing that changes is the thin veil of particles that already circles the satellite. Those particles become a cloud of grit, moving at several kilometers per second, and they begin to intersect the orbits of our lunar probes. A satellite that once traced a clean, predictable path now faces a stochastic field of micrometeoroids that can puncture solar panels or erode thruster nozzles. We have already seen how even tiny specks can scar a spacecraft's surface. In this new environment, the risk grows from a rare inconvenience to a routine hazard. Operators will have to schedule more frequent attitude adjustments, and the fuel budget for each mission will shrink accordingly. I find it hard to picture a launch window that does not include a contingency for debris avoidance. The debris does not stay put. Gravity pulls the fragments into elliptical arcs that swing past the far side of the moon, then swing back toward the near side. Some of those arcs intersect the low-altitude orbits reserved for communication relays. A relay that loses a panel to a high-speed impact will drop its downlink rate, and the whole network may need to reroute data through a more distant node. The latency increase may be only a few seconds, but for a crewed habitat that relies on near real-time telemetry, it is a palpable pressure. Planned lunar bases sit on a surface that was already covered in fine, electrostatic dust. An impact throws fresh dust into the air, and the new dust is coarser, heavier, and more abrasive. Habitat airlocks that were sealed against the original regolith will now have to contend with particles that can jam seals and wear down filters. Engineers have designed dust-repellent coatings, yet those coatings were tested under a static dust environment, not under a constant rain of high-speed grains. We don't really know how long those coatings will survive the new onslaught. Radiation exposure is another side effect. The impact ejects material that can momentarily block the thin lunar exosphere, altering the scattering of solar particles. A temporary increase in high-energy particles could raise the dose received by habitats, especially those that rely on thin shielding. Habitat designers will likely have to add extra mass to walls, which in turn raises launch costs and reduces payload margins. The trade-off feels like a never-ending balancing act. Navigation on the moon already depends on a network of beacons that reference the moon's center of mass. A large crater reshapes that mass distribution, shifting the center by a fraction of a meter. For a rover that uses inertial navigation, that shift translates into a drift that accumulates over kilometers. The drift is small, but over a month-long traverse it could misplace a scientific instrument by tens of meters. Survey teams will need to recalibrate their maps more often than they planned. Communication with Earth also suffers. The impact creates a plume of ionized gas that can refract radio waves. When the plume hangs over the line of sight, a brief blackout can occur, lasting seconds to minutes. Ground stations will have to anticipate these windows and buffer data, adding complexity to mission control software. The software already juggles many variables. Adding a stochastic blackout schedule feels like a quiet irritation. Mitigation strategies are now on the table. One idea is to launch small, clean-up craft that chase the debris and use electrostatic nets to capture it. Those nets have been tested in low Earth orbit, but the moon's weaker gravity and lack of atmosphere change the dynamics. The nets may need to be larger, or the craft may need to fire thrusters more often, burning precious propellant. I find it hard to picture a fleet of such craft staying operational for years without resupply. Another approach is to harden existing satellites with multi-layer shields, similar to those on interplanetary probes. Adding layers increases mass, and every kilogram added to a lunar orbiter reduces the payload it can carry. The trade-off between protection and capability becomes a constant negotiation between engineers and mission planners. In some cases, the decision may be to retire a satellite early rather than risk a catastrophic failure. Policy discussions have already started in a few diplomatic circles. The Moon is governed by treaties that assume a relatively stable environment. An impact that throws debris into Earth-crossing trajectories raises the question of liability. If a fragment from the lunar cloud strikes a satellite in geostationary orbit, who is responsible? The current legal framework offers little guidance, and nations are beginning to draft amendments that address lunar debris incidents. International coordination will be essential for any mitigation effort. A single nation cannot monitor the entire debris field, nor can it afford to launch enough clean-up craft on its own. Joint observation networks could share radar data, but the data streams need standard formats, and that requires agreement on protocols. The negotiations feel slow, as if each side is measuring the dust on a tabletop before deciding where to place their hand. Funding agencies are also re-evaluating their budgets. The cost of reinforcing habitats, adding shielding, and launching additional mitigation craft may divert money from scientific payloads. Some projects may be postponed, while others are scaled back. The ripple effect reaches even the educational programs that rely on a steady flow of lunar data. It is a quiet, pervasive shift in how we allocate resources. Even the psychological aspect of crewed missions is affected. Astronauts train for a stable environment where the Moon's surface is a known quantity. Introducing an unpredictable debris cloud adds a layer of uncertainty that can erode confidence. Mission commanders will need to incorporate contingency drills that simulate sudden loss of communication or unexpected dust storms. The drills feel more like rehearsals for a problem that may never happen, yet they cannot be ignored. In the end, the Moon's altered state forces us to rethink the simplicity we once attributed to operating there. Each subsystem, orbital, surface, communication, legal, must be examined under a new set of constraints. The effort resembles a series of small adjustments rather than a single, sweeping overhaul. A sensor on the far side of the Moon records a faint, steady hiss of particles striking its antenna, a reminder that the environment is still settling. Ground-based telescopes have been scanning the night sky for decades, their mirrors catching faint glints that drift past Earth. Each night the observatories log positions, brightness, and motion, feeding a catalog that grows slower than the stars themselves. The data sit on servers, waiting for a pattern that might hint at a future collision. Space-based surveys add a different perspective, hovering above the atmosphere's blur. Infrared sensors feel the heat of a rock that reflects little sunlight, revealing objects that ground eyes miss. The orbiting platforms sweep wide swaths, returning pixel by pixel maps that complement the terrestrial record. Together they form a net, thin, but the only one we have. Radar is the next step, a pulse that bounces off a moving target and returns with a faint echo. By timing that echo, we gauge distance to within meters, and by measuring its frequency shift, we infer speed. The technique turns a distant speck into a three-dimensional shape, exposing ridges, boulders, even loose regolith on the surface. It feels like touching a phantom with a stick. When a trajectory shows a possible impact on the Moon, the clock starts ticking. Early warning timelines for lunar threats are measured in years, not months. A detection today gives us a window to plan, to test, to act. If we wait until the object is a few million kilometers away, the options shrink dramatically. I find it hard to picture a scenario where we react after the rock has already entered the moon's sphere of influence. One of the simplest mitigation ideas is the kinetic impactor, a spacecraft that slams into the asteroid at high speed, nudging it ever so slightly. The physics are straightforward, momentum transfer, but the engineering is anything but. The probe must hit a target moving tens of kilometers per second, with a timing error of seconds. Tests on small bodies have shown the method works, though the exact change in orbit can be difficult to predict. The result is a tiny shift, perhaps enough to miss the moon by a few hundred kilometers. A more patient approach is the gravity tractor, a spacecraft that hovers near the asteroid and uses its own mass to tug the rock over months or years. The craft fires its thrusters to stay in place, the tiny gravitational pull slowly altering the asteroid's path. The method requires a reliable power source and a stable orbit around an irregular body. It feels almost absurd, using a feather to move a mountain, but the calculations show it can work if we have enough lead time. Both kinetic impactors and gravity tractors need precise knowledge of the asteroid's mass, composition, and spin state. That is where radar and optical observations converge, providing the parameters that feed simulation models. The models run on supercomputers, iterating thousands of possible outcomes until a probable path emerges. We don't really know how a porous, rubble pile asteroid will respond to a hard hit. The uncertainty remains a stubborn part of every plan. International collaboration is not optional. It is the only realistic path forward. Space agencies share telescope time, exchange radar data, and co-fund mission concepts. The coordination resembles a lab notebook passed between colleagues, each adding measurements, each correcting the record. When a threat is identified, the agencies must agree on a response, allocate launch windows, and synchronize communications. The process can be slow, hampered by bureaucracy, but the alternative, each nation acting alone, would leave gaps in coverage. Funding cycles influence how quickly new technologies move from concept to flight. A proposal for a next-generation infrared survey may sit on a committee table for years before a satellite is built. In the meantime, existing assets are repurposed, their sensors recalibrated to look for smaller, faster objects. The reality is that our monitoring system is a patchwork, stitched together from instruments that were not originally designed for planetary defense. Emerging technologies promise to tighten the net. Small satellite constellations could provide continuous coverage, each unit acting like a pixel in a larger picture. Laser ranging stations on the moon itself might one day measure the distance to passing rocks with centimeter precision. These ideas are still in the prototype phase, and their performance under real conditions remains to be proven. I don't feel comfortable claiming they will solve the problem outright. Even with perfect detection, deflection remains a gamble. The kinetic impactor that succeeded on asteroid Dimorphos showed a measurable change in orbit, yet the outcome depended on the impact angle and the target's internal structure. Replicating that success on a larger, more irregular body may yield a different result. The gravity tractor concept has never been tested beyond simulations, leaving a gap between theory and practice. The timeline for a lunar impact scenario is compressed by the moon's lack of atmosphere. An incoming rock will strike the surface at full speed, creating a crater in seconds. There is no chance for a natural braking process. That urgency pushes the warning window earlier, demanding that detection happen while the object is still in the inner solar system. The farther out we can see, the more options we retain. To extend that view, astronomers are developing wide-field optical surveys that can spot faint objects at greater distances. The surveys operate continuously, scanning the sky night after night, building up a history of motion that can be extrapolated forward. The data streams are massive, and sorting through them requires machine learning algorithms that flag anomalies. The algorithms are not perfect. False alarms waste time, but missing a genuine threat would be far worse. Radar facilities on Earth, such as those in Goldstone and Arecibo's former site, provide the high-resolution follow-up needed after an optical detection. By bouncing radio waves off the object, they can resolve surface features down to a few meters. The echo strength also hints at density, helping to distinguish a solid iron rock from a loosely bound pile of dust. That distinction matters when choosing between a kinetic impactor and a gravity tractor. In practice, a mitigation mission would likely combine several techniques. An initial kinetic impact could provide a course adjustment, followed by a gravity tractor that fine-tunes the trajectory. The sequence would be planned months in advance, each step calibrated by fresh radar measurements. The choreography demands precise timing, like a laboratory experiment where each reagent is added at just the right moment. The human element cannot be ignored. Decision makers must weigh the cost of a mission against the probability of impact, and the public's tolerance for spending on a threat that may never materialize. The debate often circles back to the same question: do we invest now or wait until the danger is undeniable? The answer is rarely clear, and the uncertainty lingers like dust on a bench. Ultimately, our ability to protect the moon rests on the same tools we use to study it: telescopes, radars, spacecraft, and the people who operate them. The instruments are imperfect, the models are approximations, and the timelines are tight. Yet each observation adds a line to a growing ledger of knowledge. Each test flight writes a new entry in a logbook that may one day keep a rock from striking a silent world. I watched the latest radar return flicker across the screen, the speck of an object rotating slowly, its surface catching a glint of the transmitter's pulse. The echo faded, leaving a faint imprint that hinted at a ridge about 20 meters high, just enough to remind me that even the smallest details can shift the balance of a future decision. The moon has always been more than a pale disk in the night sky. It sits like a quiet gauge, catching the faintest tremor of a wandering rock before Earth feels the blow. When a meteoroid grazes the lunar surface, the impact throws up a plume of dust that spreads across the thin exosphere, a reminder that the satellite can act as an early warning for larger threats. We have already placed a few seismometers there, listening for the subtle shiver of a distant strike, and those tiny tremors become data points in a larger safety net. Our planet's own scarred record tells us why that net matters. The layer of iridium-rich clay at the KPG boundary marks a sudden, planet-shaking collision that erased the dinosaurs. A century-old flash of light over Siberia left a shallow crater and a forest of fallen trees, a reminder that even modest projectiles can reshape ecosystems. I find it hard to picture the exact moment the shock wave rolled across the continents, but the geological imprint is unmistakable. Those ancient wounds still guide the way we think about future hazards. If the moon can register a strike that Earth misses, it also offers a place to test deflection techniques without endangering life. A controlled impact on the lunar far side could demonstrate how a kinetic interceptor changes an object's trajectory. The experiment would be simple in concept: hit the rock, watch the path shift. But the practical details are tangled in orbital mechanics and material strength. We don't really know how a porous asteroid would behave under a high-speed blow, and the data we gather will be imperfect, yet it would be a step toward a more reliable shield. Ethics creep into the discussion the moment we consider altering another world. The same instruments that monitor lunar quakes could also become tools for contamination, spreading Earth microbes across an untouched regolith. Some argue that any human footprint on the moon is already a breach, while others claim that responsible stewardship means we must protect both the moon and Earth from each other's debris. The line between protection and intrusion blurs when we plan to build habitats, extract water, or even launch rockets from the surface. I sometimes wonder whether our desire to use the moon outweighs the duty to preserve its pristine state. Future lunar missions are already sketching a new kind of presence. Robotic rovers now trundle across basalt plains, their wheels stirring up fine grains that settle on solar panels like a thin veil. A small crude outpost, perhaps perched near a permanently shadowed crater, would rely on local ice for drinking water and fuel. The engineering challenges are tangible: thermal cycles that swing from blistering heat to bone-cold darkness, dust that infiltrates every joint. But each obstacle also teaches us how to live in an environment that is not Earth. Those lessons will inform how we design habitats on Mars or on asteroids. Beyond the technical, there is a softer, almost invisible shift that begins when people realize the fragility of their orbital neighborhood. When headlines mention a newly discovered rock the size of a mountain, the public's reaction often flickers between fascination and fear. If we frame that fear as a call to vigilance, it can become a catalyst for education, for a culture that treats the sky not as an infinite backdrop but as a shared arena. Schools could use simple experiments, dropping pebbles into water to model impact craters, to illustrate how energy spreads. I admit it doesn't quite make sense when you say it aloud. A classroom can't replicate a multi-kilometer asteroid, yet the analogy holds enough weight to spark curiosity. A vigilant mindset also demands that we keep watching the heavens with instruments that never sleep. Ground-based telescopes scan the night for moving points of light, while space-borne sensors catalog the faint glow of objects that slip between the stars. The data streams are massive, and sorting the harmless from the hazardous requires algorithms that balance speed with caution. Occasionally, a false alarm triggers a brief scramble, a reminder that our systems are not infallible. Those moments teach us humility, and they reinforce the need for redundancy: multiple eyes, multiple methods, multiple checkpoints. When we talk about planetary protection, we often focus on the risk of bringing alien microbes back to Earth, but the reverse is equally unsettling. A launch from the moon could loft dust that eventually drifts into Earth's atmosphere, a subtle exchange that blurs the line between natural and artificial. The probability is low, yet the principle is clear. Any alteration of one body can ripple through the whole system. This interconnectedness is why some scientists argue for an international charter that outlines permissible activities on the moon, much like treaties that govern the seas. The idea of stewardship does not require grand gestures. It can begin with a simple observation. A researcher noting the way a fresh impact scar reflects sunlight differently from older terrain is already contributing to a body of knowledge that may one day prevent a disaster. Those incremental notes accumulate, forming a map of risk that future generations can consult. I sometimes sit in a quiet control room, listening to the soft hum of computers processing orbital data, and I feel the weight of that collective record. In the end, the moon's role as a sentinel is both practical and symbolic. Its silent surface bears the marks of countless collisions, each one a reminder that space is not empty but filled with moving bodies that can change our world in an instant. By paying close attention to those marks, by learning from the scars left on Earth, and by treating the moon with respect, we cultivate a habit of careful watching. That habit may be the most reliable shield we have against an unexpected strike. The dust that settled on the rover's solar panel this morning caught the first sliver of sunrise, turning the edge of the panel into a thin, glowing line.